This is the Graphing Quadratics Part 2. We previously had the video that was graphing quadratics in the form of y equals ax squared, and that's it. So we're going to look at another format. In Part 2, we're going to be looking at quadratics that are in this form. Y equals a times the quantity x minus h. Now, that is a quadratic. It's a factored quadratic, and in fact, if I were to multiply this out, this binomial that's being squared, of course we'd get x squared minus 2xh plus h squared, and then we'd multiply the a and we'd have it all written out in standard form. But right now I want us to keep it in this factored form, and we're going to look at ways to interpret this graph when a quadratic is written in this form. To do so, we're going to do it with specifics. We're going to look at a graph where a is 1 and that h, and remember this is very important here, that this says minus x minus h. It's not x plus h, but s minus h. So I'm x minus 0. My x is 0. My h is 0. Well, when we simplify that, that's just x squared, which is the graph that we've been looking at, that we looked at in the previous video. And so here it is again, this beautiful parabola that has a vertex at 0, 0, that has a line of symmetry at x equals 0. And in this case, we're looking at the way this is written, and we go, oh, I can see that h equals 0 here for just this letter, this way the formula is. And I notice that, oh, my line of symmetry is x equals 0. So I wonder if, now we talked about the correlation between the line of symmetry and the coordinate for the vertex, but I see that I've got this h equals 0 as well, and I wonder, and we'll look through some next couple of videos we're going to look at, if there is a correlation between those two terms. Let's look at another specific graph, because you can look at the previous graph on how to graph this first equation. I've already taken care of that in the first video. Now let's look at this one here where I've changed. I still have an a of 1. In our previous video, we know that this changing the a is going to make it wider or skinnier. I'm just going to be changing my h in this case. So this time, my h is 3. It's what I am subtracting from the x. So I've got h equals 3. I'm going to start out by doing it just like we did in the previous video of making a t-table, and we'll just stick with the same inputs that we used before. We used -3, then we did -2, then we did -1, and I'm just evaluating because -3 minus 3 is 6, -6 squared is 36, -2 minus 3 is -5, -5 squared is 25, so that's why I'm doing all these out here. I can keep doing this, and I go all the way, I get -3, -2, -1, 0, then 1, then 2, and 3. And I go, okay, great, but let's look at these numbers. Do I see that symmetry that we've talked about before, this repeating of any of these numbers? I don't see that. So that doesn't help me find my vertex. I need to be able to see where all of a sudden I am having repeats of my outputs, but I don't see any, which means I'm going to need to do more evaluations since I've only got these terms that seem to be starting off big and getting smaller or getting closer to 0, depending on the direction you're looking at them. So I need to evaluate more, and so I'm going to evaluate now at 4, 5, and 6. And when I do 4 minus 3, I get 1. 1 squared is 1. 5 minus 3 is 2. 2 squared is 4. 6 minus 3 is 3. 3 squared is 9. And now all of a sudden I go, oh, look, I've got right here the numbers 1, 4, and 9 that were up here, 1, 4, and 9. So therefore I know that right there is the turning point, my vertex, and I'm going to graph. Now I'm not going to graph all of these terms. I don't need to graph all these points. First of all, my graph doesn't even go up to 36, doesn't even go up to 25. It doesn't even go up to 16. So I really can't even start graphing it till I get to this 0 and 9, 1 and 4, 2 and 1, 3 and 0. Okay. Well, I could do that, but I also want us to recognize that I'm going to graph this vertex first, 3, 0. So I graphed the vertex right here. Now, I could just graph these ordered pairs, 0 and 9, and 1 and 4, and 2 and 1. But I also want you to realize that there's what I like to refer to as the Parabola Dance, which says from this vertex, go over 1 unit, and then up 1 squared. This is so long as my A is 1. This is the dance for when A is 1. I start at the vertex and I go over 1 and up 1 squared, and what do you know? That's where there is a point. So there it is. Went over 1, up 1 squared. Now let's go back to the vertex, and the next one is we're going to go over 2 and then up 2 squared, which is 4. And there it is. And now the next one is I'm going to go over 3 units and up 3 squared, which is up to 9. And there it is. We also talked about that line of symmetry through the vertex, so I'm going to put my, whoops, where is it? There it is, line of symmetry. I have my line of symmetry going right through the vertex there. And now I can draw the other points as mirror images. So I'm not even really looking at my t-table now. I'm just doing, oh, whoops, this is the line of symmetry, x equals 3. And oh my goodness, the line of symmetry, whoops, sorry. The line of symmetry right here, x equals 3, and h equals 3. That seems to be an interesting thing going on. I got my other points, and now I'm going to carefully draw my curve. I want you to be thinking about how that parabola moved, where it used to be this blue and is now moved over here to that pink, where it is in pink. And you might describe it that I moved the parabola. Every single point on this parabola got moved 3 points over. It's like I picked up this whole blue parabola and then just moved it 3 points to the right. And that's exactly what it appears to have done. And that might have something to do with this h equals 3. Let's look at the third one and see if we can figure out what's going to happen before we see it. Well, right here I have x plus 5. Don't forget the formula says, what are you subtracting from x? And so when I say I'm not subtracting, I'm adding, but adding is the same thing as subtracting a negative. So my h is actually negative 5 because I'm subtracting a negative 5. I can write that up there like that so you can see. Well, what this tells me, if I think about the pattern that I saw from these two, is that I moved it from 0 to 3, so I took the vertex from 0, 0 to 3, 0, which might make me believe that when I do this one, I'm going to do over to negative 5. But what I need to do is I could do a t-table of values and do all these things out, and I can't find it. I'm still looking for my vertex, and all of a sudden, there it is. I see my vertex right here, and it's exactly as I predicted. I was believing I was going to move it to negative 5, and sure, it's negative 5 and then 0. So we can see that when I graph that, I get that point, negative 5, 0, right there. Now I'm going to graph a bunch of points to the left and to the right of it. So I have points going up there, and I'm going to also want points, my line of symmetry. It goes right through the vertex, and I'm going to do my mirror image of points. Oops, sorry. Oh, whoops, the line of symmetry, and then my other points. Now I'm going to graph very carefully, doing a nice curve. Now I'm going to speed that up just a tad there. And now we have the parabola. And how would you describe this move from where the blue parabola, the parent parabola is, to where the green parabola lined up? Well, it moved negative 5 units. It moved 5 units to the left. The entire parabola just got picked up and moved to the left. So if we were to describe this pattern, we would say that when we have in the equation, I should say y equals a times the quantity x minus h, we can see that what's going to happen is, oh, don't forget it's minus, that the parabola is going to move either to the left or to the right h units, whatever h ends up being. Not only that, but the line of symmetry will always be x equals h. So this is the second of the two videos showing you about graphing quadratics.